Hello and welcome. It's me Prakash Gaire. Today I'm going to perform an experiment on the topic Newton's ring experiment to determine the wavelength of light used using virtual platform. Here I have prepared a report. First of all, sharing screen. I'm sharing screen. Okay. I have prepared a report like this. Here I have it has some of my information and here is the table of content. In this report, I have mentioned abstract, keywords, apparatus required, introduction, literature review, theory, observation table, calculation, error analysis, precautions, result and conclusions, advantages of virtual lab, limitations of virtual lab, acknowledgement, references, and at last appendix. First of all, abstract and keywords in this experiment are plano-convex lens, interference due to thin film, division of amplitudes, bright and dark fringe. In this Newton's ring experiment, we have fringe in the form of rings. Circular fringes is obtained. And for this experiment, we need, that means apparatus requires a sodium lamp is monochromatic source of light, plano-convex lens, glass plate and vernier microscope to take the reading of that diameter of the ring obtained. And here I have mentioned some introduction, literature review, and now we move to the theory of this phenomena, means interference due to thin film in Newton's ring experiment, condition for formation of bright and dark fringe. Before going into this, I want to take some. Here is the experimental setup. For this experiment. First of all, we want to discuss about the component of this experimental setup. For this, I have some. Here is the file. Okay, this is the experimental setup for Newton's ring experiment. Here we use the sodium lamp as a source, and these rays are made parallel by this collimating lens L, then which are incident on this glass plate, which is inclined 45 degree to the horizontal, and after incidenting on the glass plate, the ray bend to directly incident normal to this plano-convex lens, and go the refraction takes place. And here is in between air film is formed with the combination of this plano-convex lens and plano glass plate. The air film of thickness T is observed here. We can see the film of air is formed between this plano-convex lens and glass plate, which play an essential role to form the interference pattern on the microscope. And interference is obtained in this microscope, which is like this ring formation. We can see central dark fringe, alternative dark, bright, dark, bright, bright. This type of interference pattern is obtained in the microscope. And for this, we want to go into detail of this phenomena. This is the geometry of plano-convex lens. Before going into this, I want to emphasize this phenomena. Here we take a ray of C, name as C, incidenting on this plano-convex lens, and at point D, the border between this glass and air, the reflection and refraction takes place at point D. And with this phenomena is also called division of amplitude, and some part of the ray goes down to the boundary between this air and glass, and again reflection takes place at point J. Here is the point J and D. Reflection takes place at point D and at point J. So these two rays 1 and 2 get overlap, means superposition of these two rays are monochromatic, since we have derived these two waves from a single parent wave with the application of division of amplitude at point D. So after the superposition of these two ray 1 and 2, we get the interference pattern on the microscope here, just like this. The fringes are circular fringes are obtained because of this geometry of this plano-convex lens. At the point of contact, means at the center, we suppose this point as O. At point this O, the thickness of air film is 0, means there is no air between these two boundary, this glass plate and this plano-convex lens. If we move forward outward, this O to Q, towards the direction of Q, if we move towards the direction of Q, the thickness of air film gradually increases. So the thickness, the loci, the point, the locus of point, forms the circle here. Constant thickness T forms the circle here. So resulting the circular fringes means here is the geometry of plano convex lens is such that the point, the thickness at this point and at this point means in a circle that is fixed, so that we obtain the circular fringe. Now we go into this theory. Here is the the reason behind this constructive and destructive interference means this bright and dark fringe is because of this optical path difference. We have the relation. The optical path difference is given by 2 mu t cos r minus lambda by 2. Here in our case, the film is formed with the air, so mu is 1 for air, and cos r, the ray after incidenting from glass plate, means the ray incidenting in this plano-convex lens is perpendicular, so cos r equals to 1 since r equals to 90 degree. So we obtain this optical path difference as 2t minus lambda by 2. For constructive and destructive interference, we have the condition. For constructive interference, the optical path difference must be integral number of full waves. So we have the relation as path difference equal to m lambda. After solving this, we get this 2t equals to 2m plus 1 lambda by 2 for bright fringe, condition for bright fringe. And similarly, for destructive interference, for minima, we have the relation, this optical path difference must be odd integral number of half waves. So giving this result 2t equals to m lambda for dark fringes. If crest of one wave overlap means superpose with trough of another, they interfere destructively. It means if the two waves are out of phase, they interfere destructively. Now this is the relation. This bright and dark fringe relation gives us the relation between this thickness and wavelength. For which thickness the wavelength of light used is can be obtained. And similarly, now we need to find the relation between this ring diameter and wavelength, that means r and that lambda. And for that, we have this geometry of this plano-convex lens. So using Pythagoras theorem in this geometry, we get the relation between this radius of that ring, and the thickness of this air film. After knowing the radius, we can easily find the diameter of that ring. Diameter, we have the relation diameter 2 times radius gives the diameter. So we have the relation is this. Using 2.3, we get 2.4 like this. And for a nth ring, we get the relation this. And for nth ring, we get the similar relation. After solving these two relation, we get the relation of for wavelength to determine the wavelength of light used using the diameter of the ring found in the microscope. And observation for this experiment is, first of all, we need to find the Vernier constant. Vernier constant gives the precision of that instrument. Here in this condition, we have this Vernier constant at 0.001 centimeter. And for our convenience of calculation, this dn minus dm square, dn square minus dm square, I choose consecutive rings, means first ring with difference between second and first, third and second, fourth and third, like that. In that pattern I choose. And the observation is taken like this. First of all, I want to show you the experimental setup which is provided in virtual platform. Here is the experimental setup. The observation is the observation can be taken is here. I will say it. First of all, the medium is air. We are keeping the film of air between that plano-convex lens and glass plate. Since we are not going to measure the refractive index of the material, we are just measuring the wavelength of light used here in our condition. Light source is sodium, and let turn the light on. Okay. And radius of lens in my condition, in my this experimental set of observation, I have choose this wavelength, a radius of lens is 90 centimeter. It is better to take larger radius of lens since we get the separated ring, means larger radius of ring we obtain. It is easier to it is easy to find the diameter of this ring found in the microscope. And here we take the reading edge by changing the microscope position. There is, first of all, I want to go into the observation table again. Here is the observation table. Okay. In observation table, we have this Vernier scale, and we need to find the left and right, resulting the after subtracting this left and right, we get the diameter of the ring formed. So for left and for right, there is main and Vernier scale reading here in our experimental setup. And after differentiating these two value, we get the diameter of ring, and squaring them, we put this value in equation above 2.5 to get the wavelength of light used. First of all, to find the diameter of the ring formed, first of all, keeping the microscope position in left, for ring number here, I have taken the diameter of up to 8th ring, means counting this ring, first ring, second ring, third ring, similarly up to 8th ring I have calculated the value. So first left and then right, we resulting find the diameter of the ring. Here in this experiment, we do like this. First of all, okay, light is on, microscope position, change the microscope position. Okay, first of all, we are going to find the reading of right side of the ring, first ring. It is found to be, here is the scale of main scale and Vernier scale. So the gap between these 3 and 4 is 20 scale are present between these 3 and 4. So here is this 2.9, 2.8, 2.7, 2.6. This is 2.5 longer scale, and 2.5 this one, and 2.4 this one. Means here in our case 2.35 the main scale reading, and Vernier scale overlap 8.30, 30, or accurately 31, 32, 33. Precision at this point 31 is directly overlapped with the main scale reading. So we can take the Vernier scale reading as 30 and main scale reading as 2.35. This is 3 and 5, 3 in between 3 and 4. Here is a line of 3, 5. So 2.35 main scale and Vernier scale at 33, resulting the total measure for this left side of the ring. And similarly for right side, we go like this. For right, okay, for right, here is the reading is, this is 2.5 line we know, and 2.5 main scale is 2.5, and Vernier is overlapped at 2.5. okay, 2.5, 10, 20, and 25. At 25 we can see the overlap between this main scale and Vernier scale. So we get some calculation like this, some observation for second. Similarly for second ring, we take the reading of this left side of the ring. For this is for second ring. Okay, here it is. Here is second ring of reading of left side, second ring. And similarly take the reading from this main scale and Vernier scale. Similarly for right side, yes, for this we take the reading of this second ring, and similarly for third ring right side and fourth ring right side. Similarly we can proceed this same thing to obtain the observation up to 8th ring. Here I have taken left and right of this up to 8th ring, and finding the difference between this left and right, resulting the diameter of that ring, and squaring that diameter, and taking the gap between this 0.04 and this 0.015625, means this consecutive second ring diameter subtracting with first ring diameter, third with second, fourth with third, similarly in that way. And using this difference relation, means difference of this dm square minus dm square, in this relation to 2.5, r is radius of that plano-convex lens. In our case I choose 90 centimeter, and n minus m is 1. Since we are taking this n equals to m plus 1, so that difference is 1. So after calculating this wavelength, we get the mean wavelength value as this 5889 angstrom, which is very close to our actual value. Actual wavelength of sodium light is 5893, which is the mean of that D1 and D2 line present in the sodium light. And error, I have calculated percentage error here, and precautions for this experiment is, if we are conducting a real lab experiment, all the glass surfaces must be cleaned before recording the values. The microscope should be parallel to the edge of the glass plate. The reading on that Vernier scale must be taken very carefully in our special experiment, and result and conclusion in this experiment is this film, a thin film of air is introduced with the help of plano convex lens on glass plate. Central fringe is observed dark since t equals to 0 at center. With the help of equation 2.5, we will discuss this central dark fringe later on in appendix. And the observed value of wavelength is 5889 angstrom. Advantages of virtual lab experiment and its limitation, I have mentioned some of point here. And acknowledgement, I wish to thank all those who have so kindly helped me with the preparation of this work. In particular, I acknowledge our head of department of Central Department of Physics for his encouragement of this my work. And references in this experiment, I use this book by Subramaniam, a textbook of optics. The figure I have shown, I have attached in this report, is also taken from this Subramaniam book. Yes, I have shown you the figure like this. Okay, and some other references I have chosen, and some appendix questions are just Viva questions with their answers. I have attached a few of the questions we discuss here. What do you understand by the interference of light? We know the interference of light, the phenomena of redistribution of light energy due to the superposition of light wave from two or more coherent sources is known as interference. The source must be coherent here. Coherent means the wave need to keep some constant phase difference in long time, means long distance, time and distance. Then they need to keep that constant phase difference. Here in our case, the wave from these the parent rays C gives to these coherent 1 and 2 coherent rays, since they are formed with the help of division of amplitude at point D. Okay, that is interference, the redistribution of energy. Now, second question is, what do you understand by coherent source? Yes, we have discussed this again. If two or more wave maintain a constant phase difference over long distance and time, then they are said to be coherent. This is the essential condition for obtaining interference pattern. In general cases, we do not see the interference pattern because the wave interacting are not coherent in nature. So to obtain the interference pattern, we need to maintain this essential condition, means coherent source must be there. Okay, third question is, why are Newton's rings circular? Newton's rings are circular. We have already discussed this question also. The locus of points where the air film has the same thickness then fall on a circle whose center is point of contact. Center is point of contact means at point of contact the thickness is 0. Since the fringes often depend on the thickness of the air film, therefore circular fringes are obtained. Okay. Now fourth question is, why is central ring dark? The optical path difference is given by 2t minus lambda by 2. At the point of contact t is equals to 0, there is no air present between that plano convex lens and glass plate. So the wave reflected from the lower surface of the air film suffers a phase change of pi, while the wave reflected from the upper surface of the film does not suffer such change. Here in figure we can understand this better. The wave from upper surface and lower surface, upper surface wave do not suffer that phase change, and that second ray suffers the pi change, means phase change of pi, means resulting they are out of phase at point of contact, this at central point. Thus the two waves are at the center are opposite phase and produce a dark spot. To understand it clearly, we can see the figure below. Means this pi phase difference means equals to the lambda by 2 path difference. This is the equivalence relation between path and phase. So the central ring is dark. This is the, yes, this much is my report I have prepared. Okay. Now, okay, thank you. This is the report I have prepared. Okay, thank you.